gel from Dubai and Brandon and Brandon from Brisbane, but just when you're ready, feel free.
We'll get going. Welcome everyone to Facade Engineering for Beginners. This workshop is going to be born out of a request from a couple of people over the last couple of months to sort of try and have some sort of, I guess, basic engineering terms, sort of kind of run through and explain to them so that they can kind of implement these in sort of day-to-day use. So, the agenda for today. We will be starting off with just sort of going over that focus that we've just spoken about, and then we'll be running through these series of topics here. So,
sorry, Michael.
Yes.
Sorry, can you talk closer to the microphone? It's a bit echoey in there. We can't sort of understand what you're saying.
Yep. No worries. Is that better?
Yes. Yes.
Okay. Cool. I'll try and speak more towards the microphone. And so essentially we're going to be trying to run through, I guess, kind of a typical engineering approach to probably more specifically a kind of a curtain wall situation, but we're going to jump back and forth and look at a couple of different other ideas in terms of engineering. So kicking off, the focus of today's session, as I've kind of touched on, is to avoid this pretty much. But in short, as I kind of touched on, it really is about trying to give you guys some tools for engineering for the everyday. So whether you're in the drafting team or consulting team or even the building physics team, acoustics, whatever you may do, the idea is that you may be able to have some tools that you can either implement or things that you can identify and then go and seek sort of further guidance from our engineering team to see if they are okay. So the first thing we're going to touch over here is what's called limit state design concept. So this is just a kind of a brief intro on how within at least habit and particularly in the engineering industry we look at problems. So the focus of it is essentially to generate the loads. So what is being applied to my facade. And the way we do these loads is we increase these loads by safety factors. These loads obviously give us actions on our structure, bending, compression, tension, whatever you may like. And then what we do is we find what the capacity of that member that the loads have been applied to is. And then the very last step is to check that that capacity, which we have reduced, is still greater than our load which we've brought up, if that makes sense. So it's a very safe approach, but this is how we sort of do it these days. On this, in terms of designing and capacities, what am I talking about? And so there's really two key things that we look at when we're looking at a structure or a piece of glass or even the smallest element. So the first is strength. So at absolute limit, we need to make sure that it's not going to break, it's not going to fall off, hurt someone, anything like that. And the second one we look at is serviceability or deflection. So as you can see in this picture here, this is from the Apple Store, Fifth Avenue in New York, where a little man on his snowblower ran into and smashed a $450,000 piece of glass, which is good. And this over here showed a bending test of a piece of glass. So you can see there's quite a bit of deflection going on there. Hopefully you can see that happening. Moving on from that, those loads I spoke about earlier, where do we get these loads? How do we work out what these are? So particularly in an Australian setting, these are all governed by standards. So just for future reference, if you were ever looking to work out what these were or want to investigate them further, we'll jump back to find this PowerPoint. But essentially, there's a series of standards which dictate standardised loading criteria that needs to be applied to buildings, facades, structures that go up in Australia and New Zealand. The next step that an engineer would take after I understand the idea of a limit state design is what we call load paths. Now, these are very important. So essentially it is tracking from the very first point of a force being or a load being applied, how does that work its way through the system, and it helps define and govern what an engineer would perhaps then check for computer. So take an example here of a typical curtain wall panel, which I've shown on the right with all of the little features marked up. If we just take our load path, this is probably in sort of general terms how it would look. So our wind pressure blows against our glass then transfers the load through probably our structural silicon, because it may be curtain wall, into our framing members, back down through our brackets, into our castings or anchors, and then eventually back into the structure. So along that path there, an engineer would clearly need to make sure that my glass is going to be strong enough to be able to transfer that load. I have enough structural silicon to resist that. A framing is not going to deflect, my brackets are adequately sized and the like. So that's what's called the load path technique, and it's something that you don't need to be an engineer to implement. It's quite, you just need to sort of logically think through how the loads transfer through the system. Now moving on to the next one, on this principle of kind of consider a typical curtain wall, we'll start moving into the next phase of our design. Now, I'm not going to go through this very in detail because I believe we've had a couple of lunch and learns on kind of glass anyway, so I'll keep it fairly high level. Essentially, from an engineering perspective, with our glass types, we have the three that have previously been identified. We have our annealed glass, heat strengthened glass, and toughened glass. But what we're really interested in these from an engineering perspective is their strength. That's really all that changes. They don't get stiffer, they don't get, the only real difference between them from an engineering perspective on the high level is the strength. Now, as you can see on the number here, if we were to say that annealed glass has strength 1, then our heat strengthened glass would be twice as strong as that, and our tempered glass or toughened glass would be 4 times as strong as our annealed glass. So when we're doing our strength calculations, we can take that into account. A little bit further on just the engineering of glass, glass being the absolute substrate, it gets taken and obviously made into new products, and it's getting touched on. But what we'll first touch on is insulated glaze units, which are very used very commonly. But one of the interesting things with these is how they behave when a load, in particular like a wind load, is applied to them. So inside of your double glazed unit, you have what's called a sealed cavity essentially. So it acts like a vacuum. The volume within that space cannot change as long as it's properly sealed. If it does, you've got a problem. Essentially, what this does is it allows, when wind pressure blows on one light of the glass, the load is transferred and shared between the two pieces of glass. So it works in an interesting way. This is, I don't need to get too far into this, but this is the equation that's in the glass standard for this load sharing. But what you'll interestingly note from it, if we look at this table down below here, is how this ratio works. So if we have 6 pieces of glass, each individual light of glass takes 62.5% of the wind load. Now, it's a little bit funny because if you add that up, it means that the total wind load being applied to the glass is 125% of what it originally was. It's a bit peculiar, but it's just the way the standard works. Where this equation does become very interesting is as we increase the thickness of one of the lights of glass, as you can see here, through an 8 to a 10, if you observe the load ratios at the bottom, you can see that by the time we get to a 6, 12, 10, the 6 mil piece of glass is only taking 22% of the load. But the 10 mil on the other hand is taking 100% of the load. So it's kind of interesting when you can see that. So what that would suggest is that in that situation, you could actually replace that 6, 12, 10 with a 10 mil piece of glass, and it would perform structurally, if the 10 was appropriate, it would perform the same. So it's an interesting observation, just something to keep an eye out for. We've had some projects recently where there's been very large pieces of glass on Queensbridge Tower, and we are trying to achieve single thickness of outline for pretty much the whole building. Now the challenges with that is as you move up the building, you get larger size panels, or even wider size panels. And strategy that we've been looking at, Peter Buffett here in our office, is can we beef up the internal light to essentially take some of that load off the front line in order to get a monolithic 8 light or something to work uniformly across the building. So it can have some interesting applications, and observations like this one for if you are asked to substitute a glass product, you can go back and have a look at this. So again, always been becoming a consultant engineering team, but it's some interesting notes. Another unique feature of the way that insulated glaze units share the load is that from a wind blowing on the wall perspective, whether this was a 6 mil, 12 mil, 6 mil piece of glass, 6 mil, 12 mil, 10 mil piece of glass, or a 10 mil, 12 mil, 6 mil. So when we flip the lights on, the glassing will behave exactly the same. So even if the thin glass is on the outside, the load would still distribute like that. If the thin was on the inside, it would still distribute like that. So there's no change there, even though you might logically think you put glass, the thicker on the outside is going to make a difference. That doesn't matter. So moving on to the next one is our laminated glass product. So essentially with laminated glass, there's kind of really probably three things that we just keep in mind when we design is that with most of our typical interlayers, for a short-term load, like someone running into the window or the wind blowing, the two lines of glass can be deemed to sort of act together. That interlayer is very good at transferring the load through. So if you had a 13.52mm piece of glass, it's really going to act like a 12mm monolithic piece of glass, which is quite good. However, it does get a little bit more complicated under long-term loads, in particular sort of dead loads, which you might usually get in a canopy or a skylight situation. So this is still a little bit kind of high level, but essentially there's two common types of interlayers that are used at the moment, particularly and these are PVB interlayers or our SGB interlayers. Now, I won't get too far into that because there's a technical note on the internet about that, about the difference between the two, but all we really need to kind of take off from here is that SGP interlayers are quite a bit stiffer and quite a bit stronger, and they can actually contribute to glass strength. So all we look at here is that with an SGP interlayer, the two glass can be deemed to share the load, whereas with a PVB interlayer, they won't really share these long-term loads. They'll slip against one another. And so if we go back to our situation of a canopy or a skylight, that really means over a long period of time, you just have a 6mm piece of, say you have a 13.52 laminated piece of glass with two 6mm lights. Really over time, you're just holding one 6mm piece of light. So some things to think about there, because we do try and control that deflection of glass in that application, and with a PVB interlayer, that can be quite substantial and can end up with very thick glass. So there can sometimes be some capacity to use a stronger interlayer to try and sort of keep a reasonable thickness of glass, which is not going to be very green and detrimental to the visual appearance.
What does SGB stand for?
Centric glass. DuPont.
It's actually, it's like calling a tissue a Kleenex. It's a brand name, so that the generic term for that type of interlayer is called Inoplast. There's very few people who make it, so we tend to use DuPont's product, which is called Century Glass Plus.
Again, there's some knowledge of operations here at the bottom, not really all that fun or useful, but yeah. So the next one I want to touch on is...
Do you want to just maybe touch about how it's important to support laminated glass on both sides, the lights and the spacer? On your setting block, sorry?
Yes. So going back a little bit to, probably this is just a request there is, when we go glass into our framing, essentially most applications they put them on what's called setting blocks, which some of you may or may not be familiar with. But essentially they're small little hard rubber blocks which sit within the frame that stop the glass being sitting on the measure, which is not what we want. But there can be some tricks with this. There's good literature on it in the AS12AR, which is quite clear on what the requirements need to be, but one of the key points of this is touched here is that it's very important that in an insulated glass unit or even in a laminated glass unit, that block sits under both lights of glass. It can be very common to see on site, and they might just sort of push it to the back and you've got one light of your DTU sitting on your block, if you're sitting here, and the other one not. And eventually what you're doing is you're putting strain and stress into the silicon which holds the two units together, which over time can lead to the deterioration of the insulated glaze unit. So that is a pretty important one, and it can even go sometimes as far as not even seeing it on site. You might even see it on the shop drawing. Sometimes it can be quite obvious that that's not what they intend to do. So little thing to kind of keep your eyes peeled for. Was that sort of what?
Yeah, and I suppose that if you're considering a laminated piece of glass to act together, you've got to make sure that the dead load's transferred down through both. Because if you're only supporting one side of the laminate, then you're not really allowing it to act together.
Yeah, absolutely. You'll be putting the interlayer into shear, and again over time it can deteriorate. And we consider that we design our buildings for 25 to 50 years, so it's a decent amount of time for that to happen. The next topic I want to touch on here is one that may have been covered in the previous workshops, but it's about designing for safety with glass. So again, it's pretty well documented in AS12AR, but I think it can sometimes be quite simplified for everyone to be very clear on what it is. Essentially, there are really four types of safety glass. There's monolithic toughened glass, and then laminated annealed, laminated heat strengthened, and laminated toughened. That is pretty much it. There's not many applications. So with these 4 pieces of glass in mind, there's types of situations and applications that we need to consider when we use them. So whilst monolithic toughened glass might be a great safety glass, if it's falling from 50 metres off the edge of a building down onto the street, it's not really safety glass, even if they are small little shards of glass. Having that rain down on you is not really what you want. So there's some situations, as I said, put here, as balustrades where there's a significant fall, or even in the underside of skylights, even some lobby glazing. We have very large, tall pieces of glass, but we need to think a little bit more about how we use these. Now, let's quickly play this video, which again kind of highlights what a bit of what we were speaking about previously in terms of. I'll show you obviously.
Yeah.
So you see this is a piece of a big ball metal essentially. Now that is hidden in a monolithic toughened piece of glass. You can see that it's fractured in the pattern that you would expect, but I personally wouldn't want to be standing under that if it fell down on me. So that's the first one. Now the second one I believe they test here is a laminated toughened piece of glass. Now laminated toughened is great, it's strong, it's great at safety glass, but it does have one slight inherent problem, is that when it fractures into these very small particles like you've just seen here. But once both lights are fractured, it tends to behave a bit like a sheet, essentially. So as you see with this part here, it really doesn't have much, if any, strength at all once it's broken. And again, for the applications we're sort of talking about here, in particular maybe the underside light of a skylight piece of glass, if that was to then fall down on you, that may even be worse than just fragments of toughened glass breaking. And then the last one they show here is actually a SGP piece of glass, which kind of will touch back on what I spoke about earlier about the interlayer having some stiffness, in particular post-breaking. So as you can see here, it gives a good wallop. It breaks, but there's quite a bit of residual stiffness in the interlayer and at least that glass product. So the whole point of, I guess, this was just to touch on that, yes, those are the 4 types of great safety glass we have, but in terms of where we use them, we do need to think a little bit sometimes about this. What I spoke about in terms of toughened laminate breaking and falling like a sheet. The similar kind of behaviour is not observed with heat strengthened or anneal glass because the particles, larger particles, tend to lock together better. So some things like this that we can implement in art. So monolithic toughened balustrades where there's a big fall, probably not the best. Maybe a laminate toughened might be acceptable, provided it can't fall out like a sheet. So these are just some things that each of us can sort of think through and understand as we go about our day-to-day work here.
Who pushes through those requirements when there's a cost involved and it's not just a question of compliance? Because obviously most of those 4 products would be compliant, and yet we as engineers might decide that we think some more specific product would be more appropriate for a particular application. If there's a cost involved in that, how does that get pushed through? And do we succeed with that, or what happens?
I'd say typically, if we're doing our job right, we should be pushing it through at sort of, I guess, a consultancy stage in an early route to kind of design development. So when these situations come up and consultants write a glass specification or schedule, these are things that should be raised because yes, you're completely right. Whilst they may comply with code, what we can then kind of show is, sell is this is a best practice essentially. And usually, I think with a lot of these things, once you can explain to either a client or a builder the risk of not doing it, it can usually solve it fairly quickly. I'm not sure if we did much learn on it, but Stephen had an interesting project he was involved in with a balustrade over here in Carlton, where essentially it was monolithic toughened glass, apartment building on a balcony, and for a reason that may still not be fully known, suspected maybe that it had kind of been pushed in and sort of left under stress, but dash cam of captured panel was breaking, was falling into the street and narrowly missing some people. So it's things like that that I think would provide a good amount of job right from the early stage. That's where it should be pushed through. And if we're not the consultant on the job, I think definitely the engineering team and stuff like that. All this stuff later on, and that is definitely I think more of a problem when it's you're saying okay maybe it needs to be SG laminate toughened compared to whatever it was before. That could definitely add cost.
Essentially, we make recommendations to our client, and if we can't force them to take it, but we make recommendations, and then they make that decision.
I guess, yeah, of course. And my question was more, not about the process, but how successful are we in actually pushing those better solutions from an engineering perspective, better solutions through? Because I see that in acoustics every day. We make recommendations and it just gets ignored because it's not necessary for compliance.
We find that,
No, you go.
we find that it depends on the client. So owner-occupied clients are more likely to take our recommendation. But I think what also happens is the good old value engineering term comes out, and we don't have much control once we're novated to contractors.
Yeah.
So we don't really have much say then, but we just have to stick to our kind of advice and make sure that everyone's aware of why we're making that advice, and then if anything ever happens, we can go back to that advice.
Do we succeed though? Like, do we generally succeed in pushing those ideas through, or do we?
I think we do with glass.
Yeah, okay.
Generally with
Yeah.
glass we do, because people are scared of glass.
Yeah.
So people do take it up.
Yeah.
But it's a very interesting point you make, because I know with what I spoke about in terms of monolithic toughened glass breaking and falling from a great height, in the Australian standard, the way that is actually written is that as long as provided that fall is greater than 5 metres, the glass needs only be heat soaked. Whereas our specification says if it's above 3 metres, you can't use it. So you're definitely right, there is a gap between what is compliance and then what we try and push, and it's just about us, drive industry best practice and make sure that we're being safe and people aren't going to get hurt. To keep moving along with this one, I'll try and go a little bit. We're talking about just trying to touch on some definitions of glass restraint and what we mean when we hear in terms of it's a two-edge support, or it's going to be massive. It's just about trying to understand what that means. So I've had a real quick crack here trying to define what support might mean in terms of glass. We have a slide that says the support can be defined as a framing member, channel, glass-to-glass joint, or patch fitting capable of providing adequate structural and serviceable resistance to the actions applied from the glass. I don't know if it's clear, but that's sort of my understanding of it. So we'll just quickly run through a couple here. So this is a typical 4-edge support condition. So look here, you've got a curtain wall with glass in an aluminium frame. Essentially all 4 edges of the glass have either a structural silicon joint or a captive joint to hold it in place. So in this situation, pretty much all the types of glass are so we have laminated glass, monolithic, provided it's not toughened, IGGUs, whatever you like. Over the edge here is just a strand model, thanks to Eric Deng, that just shows essentially kind of the stress on the left and the deflected shape. So as you can see, what you'd expect, that it's deflecting the most in the middle, just in that kind of uniform pattern. The next one we move on to 3-edge and 2-edge support. Now, these situations come up more probably in like your lift lobby kind of areas, and it's usually where a corner junction or something where you don't have maybe you don't have a corner mullion, or you don't have, in this case, glass fins or something that want to read floor to ceiling glass. So what the considerations are here, we'll start with the 3 edges. And in both of these situations, IGUs might not be, so when I say IGU, mean insulated glaze units or double glaze units, triple glaze units, they might not be appropriate, because what we really need to do when we use our GTUs and IGUs is we need to make sure that the deflection along the edge is not too significant. It needs to be quite tight. It needs to, I won't get the exact number on, but essentially if it deflects too much, what can happen is the desiccant and the spacer here can separate from the 2 pieces of glass, and essentially IGU is useless. It may start condensating and will need to be replaced. So where possible, if you ever see an unsupported double glazed unit edge, the alarm bell should sort of be going off. So what you can clearly see here as well is that these are all for the same size panel and the same size wind load and glass thickness. So whilst our deflection on this edge is now 15 mil compared to 1 mil, it was in the middle before. If we now take away our other edge of support, you can see we get 43 mil of deflection in the middle compared to either 1 mil before or 15 mil here. So taking away those supports has a serious impact on the way the glass behaves. So in that situation over there, you're probably going to need to have quite thick glass to get it over the line. The last one.
Sorry,
Yes.
can you go back to the other slide? Can you just explain like what the different colours represent on those images?
Okay. So, as I before, the images on the left in the two cases are for stress, and the images on the right are displacement. So essentially, they're just referencing the scale here, showing what that is. So the pink, if I look at the two-edge support condition, the pink indicates displacement of 43 millimetres, whereas the blue indicates displacement of 0 mil. So essentially, the ends are staying where they are, and in the middle.
That's for uniformly distributed pressure, yeah?
Yes, this is for 1.5 kPa, 16 millimeters. So yeah, they're kind of what they're showing across. And then the last one we'll kind of go is what you might call one-edge support, which is cantilever glass. So you typically see this in balustrade panels sticking out of a channel or something. And again, as we've heard about before, you can see your deflection as you expect is uniformly peak along the top and gradually decreases. Do not use IGUs in this application. You don't need them, first of all, but it's not a good idea. And then again, thick glass can probably be expected in some situations, and probably going to need a form of toughened glass, typically to deal with the high stress that you get at the bottom here, which is indicated by this mark. The other one that kind of often comes up is what we call point support glass, or patch fitting glass, or planar glass. There's some other terms that people use, and essentially they're walls where the glass is fabricated with small holes in at locations designed by consultants and engineers, which are then fixed with these route fixings that you see here, back to posts, glass pins, whatever you like. So as you can see here, this is indicating the stress here, and now if we compare this to before, we're up around 104 MPa here, so that would not work for this thickness of glass. So that is quite common with point fitting glass, and it's why, as a general rule of thumb, it should almost always be used, it should almost always be toughened glass, because you get very high stress concentrations around the hole, and in order to deal with that, you need the strength which comes from the toughened glass, which we previously touched on. Is how many times stronger than a Neil glass? You're not allowed to answer.
What's the price?
And as you see, yeah, in the displacement, it's about 30 mil. So in this arrangement where we have 1, 2, 3, 4 patch fittings similar to that, it kind of acts like our two-edge support glass. So main takeaway from this is, as I said before, you can use IGUs with this, but they're quite difficult to fabricate. They need to be, the routers and everything need to be put in the factory and sealed around and everything so that unit acts as one. So it's not impossible, but it is expensive. Thick glass is usually can be a repercussion of this kind of system, and as I said before, tougher glass around the stress locations of the hole. Moving through our load path, as we spoke about before, now we get to our frame. So this over here is a nice little curtain wall panel that helped me prepared earlier. Speaking on the load path we spoke about earlier, there's essentially two situations going on here if we look at this piece of glass. The wind hits the glass and then is then distributed to the framing on four sides here, because we have a four-sided piece of glass, four-edge supported glass, and our dead load is carried through our setting blocks, as Alyssa identified earlier. So all we kind of really want to emphasise here is that our lateral members typically take a portion of the lateral load from the wind, as well as a vertical load from the weight of the glass. Our vertical members, and they take that both in bend in that way and bend it inwards, if you can imagine. Our mullions, or vertical members, posts, whatever we may have, they take the lateral load from the glass and wind, as well as the vertical load from the transom, but they take that in either compression or tension. If you imagine the load comes to this transom and it transfers back to the mullions, which are in turn bracketed. So for these different framing sizes, we have probably the major driver with framing is deflection, and trying to make sure that that is within acceptable limits. So there are some limitations there here you'll find them in every one of our schedules, but typically, yeah, we try to get this sort of under 20 to 25 mil at an absolute maximum, and then they're usually governed by the actual length of the member. And for transoms or lateral members carrying the weight of glass, the deflection is much stricter than for inward bending. So it's just so that we don't accidentally maybe dead load the glass below or move things so that they'll shatter. So here's just a couple of little pull-outs of some strand models. So this is what I was speaking about here. You have a transom with a uniform distributed lateral load and a couple of point loads to represent the weight of glass. This then gives you a displacement and stress. Engineers can check it through. The diagram on your right there is of what we call a mullion rundown, which is typically looked at in a curtain wall, where you essentially model a portion of the split mullion of the curtain wall with stack joints and brackets to represent the behaviour, and we can then look and check that our displacements are right, stresses are right. It also assists us in getting the loads to go on and check our brackets. Now, one of the key parts with our framing, and again it's kind of coming to talking more generally about a curtain wall application, but it's applicable to any type of construction, is that we need to consider how the building moves in respect to the facade. Because there's things that the building can do that can really hurt our facade if we're not careful. So in terms of vertical movement of the structure, there's three real things that we kind of need to consider. First one is what we call slab edge deflection. So between our lovely columns that we have here in our building, you might not really see it, but the slabs do deflect, particularly at the edge. It's usually never as much as the engineers say, but it can happen. The other one here is what's called axial column shortening. So as you build a building, particularly in a concrete building, over time, as the concrete shrinks and the load is applied, the buildings actually shorten ever so slightly. So unfortunately, if you pay for a penthouse, you're not quite going to get the same area that you thought you had when you first bought it, but that's the way it works. And the other things that we need to consider in all aspects is that when our frame members heat up, cool down, they either expand or contract like any kind of metal or material. So that can happen vertically in our frame as well. We also have horizontal movement. So between the two stories of the buildings, quite a bit can actually happen. If you really think about it, the columns are kind of no different from a mullion in a sense, and they're just blocking up the building. The first one I've got here, and I'll go over this quite highly because there's a lot of literature on this and it's quite a complicated topic, but the first is what's called interstory drift. So that is where in a wind event, the position of the slab above versus the position in our slab could actually differ slightly. So this can have an effect on the horizontal behaviour of our facade. As we touched on before, thermal expansion or contraction of the transoms in a lateral sense can occur. And we can also get this very peculiar situation where we've got called a differential settlement. So my friendly column over here that I was speaking about before, he could actually sink further into the ground than the column over here. Now, whilst we probably wouldn't realise it from a human perspective, what it can do is slant the wall. So these are all things that we need to consider. And why do we need to consider them? I guess that's the big question. And what it really impacts is this here. So this just shows a couple of images of how those things I've just spoken about can affect your facade. So look at this first one here. This is differential slab deflection. So you can see we have our curvature of our slab, as I've spoken about, and you can kind of see from this diagram here what it does to your curtain wall panels if they're properly fixed on top of the slab. Now this is not, I should say, it's not indicative of all curtain wall construction, but with the way we tend to typically do things here in Australia at the moment, this is sort of the situations you would get. So you can clearly see on this diagram on the left here that at the top, the panels are coming together, but at the bottom, they're moving apart. Now, some other ones you can see over here that have similar effect. Now, what this really does is it allows us to design our frame, essentially. So this is just a quick takeout of a deflection model given to us from a structural engineer, which shows the footprint of a building and shows all of those expected slab edge deflections that I've just spoken about. And then you can see on the right there a table from our schedule where we often at a consultancy stage will summarise this information so that a facade contractor looking at it can say, yep, okay, I can do some numbers here with my engineer, and yep, okay, my 150 capital suite or whatever can take those movements. So what it really governs is our joints. So in this particular case here, I've got a section and a plan detail which show the joints in our curtain wall foundation. On the back there, that the back joint is typically smaller than the front, so it's a small markup area there. But what those panel movements do is allow, behind a series of pretty serious computations, is to calculate what are the acceptable dimensions to have this width so that this won't accidentally come down too much and smack on top of him, or that won't completely close and completely open so that you can actually see out onto the street. So I guess all that there really is to take from this is just to understand the process. So typically those discussions between the structural engineer occur usually with a facade consultant in the early stage of the project. The facade consultant plays a role of essentially kind of sanity checking the deflections. They might flag if they go, okay, my slab edge is going to deflect 40 mil. Facade consultant might say, well, we're going to have a little bit of a problem here because it kind of goes beyond the capabilities of the standard curtain wall system. And then if it eventually gets down the line, an engineer working for a contractor who's actually building the job may do a detailed or a racking check to ensure that those systems will actually work. Tolerance. Why do we need it? This, if there's one thing you can all take away from today, that would be this next section here. I think it's tolerance is a killer in our industry. We essentially are always coming along and putting our product on somebody else's product, and how our product fits with their product is crucial to how it works. Essentially, I've got a couple of pictures here of some what you call maybe like tolerance gone wrong jobs. What you can see on the left here is a skylight job that the structural steelwork below is significantly lower than it was meant to be, and so in order to get the glass line to where it needs to be, they've just packed it up with probably 50 mil of pack in there maybe, I'm not sure. Anyway, the one on the in the middle here you can see is from a job where we're putting up some structural steelwork, I'll say some secondary steelwork to support glazing. Now, this bracket is actually fairly well designed in terms of being able to take some tolerance, but part of the way it's been installed has resulted in it being completely hard up against the top of the bracket. So if by some chance the slab this was deflected or moved down, that member doesn't have anywhere to go. And the top right here is it's what you describe as a situation where the bracket has kind of missed what it's connecting to. And from discussions with the members on that project, there's some pretty serious works that needed to be done on the site just to even get that bracket to be supported. So, essentially, tolerance is a three-dimensional issue. We need to think about it going in four ways. As I touched on before, it is governed by the structure we're fixing to, installation, fabrication tolerances, all of the above. But there are tools that we can use to do it. It's not impossible, we just need to think our way through it. So these tools are listed here are just some of the ways that we can deal with tolerance. So we've got slotted holes, hook brackets, jacking bolts, locking off washers, as well as a last resort packing. We'll get to that. So I'm just taking the example here of a standard curtain wall bracket. Now, with this bracket, it has been designed for sort of dealing with some of that building tolerance, but what we really need to look at here is this slab edge can vary quite significantly depending on where it is. So it could either be out, it could be in, it could be further down than we thought, it could be further up than we thought. And then we also have the situation where this bracket fixed off the back of our mullion needs to be exactly where our mullion is, and our mullion needs to be exactly where it needs to be. So just in case something's slightly off, there needs to be some play to move things to each side. So probably the first thing we do when we plonk our panel on is make sure we get it roughly in the right direction in a lateral sense. we can do this with our halving channel, which we have at the back there, which has been shown for the purpose of allowing us that large tolerance. The next thing we can do here is we've got some neat slotted holes in our bracket, so we can slide our bracket in and out to make sure that we get our facade to the exact position that we need, as well as lining up with this casting, which will always stay that distance relative from the slab edge. So if the slab edge is way back, this casting will be further back here. So we need to accommodate for that. And then lastly, we also need to make sure we get our level right. As I said before, the slab was much further down than we thought, it would be much further up. And if we just put our curtain wall straight on top of it, obviously it's going to be sitting on the bottom. So what we can do over there is a bit of packing. So I'm sure most people in this room are familiar with this kind of concept and topic. It's just sort of going over some of the principles we can use with it. Probably some of the best things we can do to deal with tolerance are slotted holes. But we need to be careful with our slotted holes because typically they need to be slotted in the direction that we want them to eventually resist. So in particular in a curved wall bracket, this sense here, if you can imagine your wall is here and it's pushing on your bracket, you don't really want it to move in that hole. So some of the tools we can use here are things like serrated washers on serrated aluminium brackets, or slotted holes in steel brackets, but in that case then they need to be locked off. So they involve side welding or side screwing. So these are all techniques we can use. One of the big differences between these two drawings is packing. Now, as I touched on before, packing is not our favourite thing in the world because it can lead to some problems with bending of our bolts if there's a lot of it. So the diagram on the left there is quite good. They've got some nice solid steel packers in there. On the right here, maybe not so much, but if that was to be grouted under, it may be sufficient. Now, I'm not going to pretend to try and explain this because we could have a full day seminar on it, and I'm not sure if any of us would be any the wiser, but I'll try and break it down slightly. So, are you all familiar with the term a moment or a pin connection? Just show hands if you're not, it's fine if you're not, it's a very complicated thing. Okay, cool. So essentially it's a structural engineering concept which explains a type of beam end connection or column end connection. So as I touched on, it's a really complicated topic, but there's some things that we can just kind of break it down and make it simple. And I guess the whole idea of this is that whether you're in the consulting side or in the drafting team or something, maybe if a drawing comes across your desk, you might be able to sort of identify from a couple of telltale signs what sort of connection that is, and then if you think there might be a problem with that, because of what we're about to speak about, you can maybe go and speak to the engineering team. So, really to break down, a moment connection is what we call a rigid connection, and a pin connection is what's called a flexible connection. So, I'll start with rigid connections. So, as the name implies, they're rigid. They don't allow rotation, and they don't allow translation. So, what I mean by that is if you can imagine your three-dimensional axes, you can slide in either direction and you can also rotate in either direction. So some of the telltale features of this, and this is being quite generic about it, but typically what you see with moment connections is you see very thick plate, so somewhere in 12 to 16 mil kind of thick plate. Quite often they have things like the image on the right here with gussets, which stiffen them up to really prevent them from rotating at all. Some other features that will kind of identify them are a significant amount of anchors, usually 4 at a minimum kind of, and then these anchors to be located at the extremities, as you can see from this plan diagram here. Now if I compare that to what we call a flexible connection, which is a pin connection, you see that a pin permits rotation, as it implies flexible, but it will still stop that translation. So as I spoke about, probably the best way to think about this is if I hold my ruler like this, so for the people on the phone they can't see it, and I let go at one end, it drops because I'm allowing it to rotate. If I grab that ruler and take away that side, it doesn't rotate. So it's essentially the difference kind of between pinned and fixed in terms of a rotation sense. The translation doesn't change. Telltale features here are usually thinner plate, usually up to about 10 mil. Usually you see kind of less anchors, and the anchors are more typically located along the centre line of a member, just like that little plan shows there. Now, there's lots of speaking here, but what does it mean? Why do we care? Right? So what if it's pin? So what if it's common? So the big impact that these have is on the way the beam behaves and what happens with the forces at the end. So this is a little quick strand printout to just show the condition or the difference between a fixed beam and a pin beam. So as you can see with these numbers here, for those who can see it from that distance, this is 2.5 mil and this is 12 mil. So with a pin beam, as I sort of showed before, you get a lot more deflection because the ends are rotating, so the beam is really curving quite a bit. Whereas with a fixed connection, that rotation can't occur, so your beam doesn't deflect very much, which you can kind of see from these little isotherms, which, like before, showed the deflections. The pink is a lot of deflection, the blue is almost none. So, as I kind of touched on, there's a few advantages and disadvantages of the two. Now, moment connections, if they're intended, fantastic. They reduce member deflections, they can typically reduce the size of members you need to use, and things like I spoke about before with a cantilever structure, they enable them to occur. So you can't make a balustrade stanchion with a pin connection, it'll just fall over. So you need cantilever connections sometimes. But some of the disadvantages of this are that the loads that end up being applied at the base are quite significant, and they can be very significant for the anchors that we need to hold into the structure, whether it be a slab or a steel beam. But at the same time, in some situations, they may not even be possible. The structure holding it might not be able to deal with the rotation force that the cantilever provides. So those are some of the disadvantages, and obviously you need to have kind of usually thicker plate, more anchors. The advantages of pin connections, smaller loads at the pin, or the bracket, and those thinner plates and less anchors like I spoke about. But on controversy, counter side to moment connections, you usually have larger deflection